Hi. I'm Jim Heffron. These are my lessons in Calculus 2. So we're starting a new chapter, chapter 11, very exciting. Let me speak for a couple of minutes to somebody who has not been watching the videos in sequence, but instead has sort of parachuted in here. Maybe, you did a search engine or something like that. So there were two preliminary videos, two videos that came before this, one on Taylor polynomials and one on series motivation that you're going to want to go back and watch before you watch this one. Just because it turns out that this is the hard chapter in the course. This is the chapter that folks always express feeling that they're not too sure what's happening. They feel like previous chapters they were able to draw a picture, or they could see from the physics implications that the area under the curve has got to be all that stuff. Now in this chapter, people feel that a lot less. So you're going to want to go back and watch the motivational videos, and that'll be a help figuring out what's happening now. Of course, if you've been watching all along, then you've heard my warnings that this is the chapter where people express confusion. People are coming to office hours by the fourth or fifth section and saying, "I don't know what's going on." So, word to the wise, this chapter, more even than the others, you don't want the homework to get away from you. If you have a big paper due in history and you're like, I'll just let the math go for 3 or 4 days. I don't think that's a good idea. You're going to be coming into class on the third or fourth day and saying, what the heck is happening here? So just as a comment. So not to be a downer, but trying to be realistic and trying to help a person by pointing out a couple places in the course of what we talk about today where, sort of word to the wise, watch out for this. Okay, let's get started. Okay, so we're starting the sequences and series chapter, and here we are with sequences, perhaps not surprisingly. And because I talked about Taylor polynomials, I'm going to start by talking about, for motivation, one slide worth of motivation here. I'm going to start by talking about the Taylor polynomials for a particular function. The particular function is f of x equals e to the x. I just picked it out of the air, and it's got to be centered somewhere, so I centered it at a equals 0. And again, I just picked that out of the air, and I wrote down the first 10 Taylor polynomials, and only 4 of them fit on the screen, but here they are. They show a distinct pattern. Right? So if there's a Taylor polynomial centered at a equals 0, and I decided to plug in x equals 10 into each of them. There are 10 polynomials. I decided to plug in x equals 2 to each of them. And here's the table. If you plug x equals 2 into t sub 0, you get 1 for an output. If you plug x equals 2 into t sub 1, you get 3. If you plug x equals 2 into t sub 2, you get 5, etc. All the way out to if you plug x equals 2 into t sub 9, you get 7.389. And for a person who is taking this course, who took Calculus 1 and now finds himself in the middle of Calculus 2, look at those numbers. Your first reaction, if you've been paying any kind of attention at all, is that this is a sequence that's approaching a limit. And in particular, if you write down all the decimal places you can grab, you see that e squared it says 7.389, and t9 of 2 says 7.388, but then there's a 7, so you would round it to 389. It sure looks like t9 is giving a pretty good approximation of e squared. And t10 probably giving a better one, and t11 an even better one, and etc. So we have the sense that we are looking at some kind of limiting process, and we got to write down what all that stuff means. So this section gives the definition that we need to state precisely what's happening here. Okay, the key point is, the thing not to miss about what happened on the prior slide is that the limits are discrete. The limits on the prior slide are discrete. Previously in this course, first couple days of Calculus 1, we would be talking about limits like the limit as x goes to 5 of x squared, and we decided that was 25 by trying an x. I'd stand in front of a classroom and try 4.9 and squared, and 4.99 and squared, and 4.999 and squared, and I'd get numbers that are increasingly close to 25. Likewise, 5.1 squared, 5.01 squared, 5.001 squared, and I'd get numbers that are increasingly close to 25. So I'd imagine sort of x creeping up on 5, either from below or above, and the x squared creeps up on 25. what's happening here, of course, is that the variable x is coming from the continuum. I mean, it's coming from what in grade school you call a number line. So you can, if you're at 4.9, you could always try 4.99. If you're at 4.99, you can always try 4.999. But the sequence on the prior slide has a T0 of 2 and a T1 of 2 and a T2 of 2. It does not have a T1.234. It just is, we have not defined a Taylor polynomial T sub 1.234. We just haven't. So that's to say the sequence on the prior slide is discrete. The limits that we are used to are somehow continuous. The limits that we need to define now are going to be discrete limits. So that's the difference. So why are we doing limits all over again? And it's because we're now doing them in a discrete context. So that's the explanation for what we're doing today. Okay, so we got to define what a discrete list is so we can take its limit, and then after that we will take its limit. So vocabulary words. A sequence is an ordered list of numbers. So this is a discrete list. There's an A0 and A1. There's nothing in between. You'll notice that I started counting with A0 instead of A1, and I think that's the more modern way to do it. And anyway, that's the way I'm going to do it. The list could be finite or it could be infinite. Each list member is called a term. So A0 is a term, A1 is a term, A2 is a term. Its place in the list is its index. You would say that the index of A2 is 2. And if convenient, we could start at a sequence at an index other than 0, but in the absence of any reason to do otherwise, we'll start with 0. The notation. You take the terms and you put them between rounded brackets. Okay, curly brackets. Term between curly brackets, and down here I've made a point of saying that the indices are 0 and 1 and 2 and 3. And again, term between curly brackets here, and here this is a finite list. I've made a point of describing that the indices run from 0 to 5, including both the 0 and the 5, or not including the 6, whichever way you like to say it. Okay, so time for some examples here. So let's see. The first example is where the terms are 1 over 2 to the n, and I'm going to start with n equals 0. So 1 over 2 to the 1 is the first thing in the list. Second thing is 1 over 2 to the 0, 1 over 2 to the 1, 1 over 2 to the 2, 1 over 2 to the 3, etc. Okay, I wanted to illustrate a sequence that doesn't start at 0, so I have a sequence that starts at 1 just to start somehow. There, the first index is 1, so the first term in that sequence is 1. The second term is 1 over 2. The third term is 1 over 3, etc. And obviously, the rule here is that the ith term is 1 over I. We say that when you write down the formula for the ith term, we sometimes call it a general term. Okay, so sometimes we want the sequences to start numbering at some other number. It's just simply convenient here because I don't want to have 1 over 0. I suppose you could start at 0 and call the general term 1 over I plus 1. Anyway, this is more convenient, so I did it this way. Okay, a couple of examples. So here's a finite sequence. I wrote down all the home runs that Babe Ruth hit per season. Here's the legendary season when he hit 60 home runs. And of course it's finite because Babe Ruth only played so many seasons. I mean, that's just all there is to it. The next sequence is the Fibonacci sequence. So it's been my experience, most people coming into this class know the Fibonacci sequence. So here we are, you're given the first two terms, A0 and A1 are both 1, and then you're told that to compute higher numbered term, like term 2 or term 3 or term 4, you compute that from the two prior terms by adding them together. For example, I was given that A0 and A1 are 1, and then to compute A2, you add the prior two terms, 1 plus 1 makes 2. Then to compute the next thing, 1 plus 2 makes 3. Then to compute the next thing, 2 plus 3 makes 5, and etc. Okay, and again, it's been my experience that folks know that already. I've seen that previously. This definition is called recursive because the terms recur in the definition of the next term. But anyway, the term that specifies that a sub n plus 1 is a function of other terms, prior terms. Okay, so recursive is a word that gets used on the homework sometimes. And just some more vocabulary here. So a sequence with a term-by-term difference is constant. For some number is called arithmetic. So here you're looking at difference of 3, difference of 3, difference of 3, difference of 3. This is called an arithmetic sequence. And obviously here, when you want to figure out what is the general term of an arithmetic sequence, you would say the initial term plus you take, in this case, 3 I many times. So, for instance, this the term that the sequence that I have down here, the general term is that you start with the 5 and then you multiply n times 3 because 3 is the common difference. If you're, instead of addition, if you're multiplying, so a sequence with a ratio is constant, you multiply to get from term to term for some number r, it's called geometric. So adding is called arithmetic, multiplying is called geometric. With a ratio r, an initial value a0, the general term is that ai is a0 r to the I. So you just multiply by r, you multiply by r, you multiply by r, etc. And just to have a numerical example, this doesn't say anything that the definition didn't say, but just simply to have a numerical example, I started at 1 and I multiplied each time by 10. Multiply by 10, multiply by 10, multiply by 10, etc. Next one would be 10,000. So add is arithmetic, multiply is geometric, just vocabulary words. We're obviously going through whatever happens to come up in later on in the chapter. We're listing up things that we're going to need later on in the chapter. An example of something that we're going to need later on in the chapter that might not occur to a person is this construct here, is the minus 1 to the n power construct. So it just so happens that as we move through chapter 10, we're going to see that a lot. It just happens to work that way. So we're introducing it now. And here we go. So I started here at n equals 0. So minus 1 to the 0 is 1. And the minus 1 to the 1, minus 1. Minus 1 to the 2, minus 1 to the 3, minus 1 to the 4. So it alternates, and as we cleverly call it, an alternating sequence. This minus 1 to the n can be used in a number of ways, and so I'm just going through a couple of ways just to illustrate that it has a variety of applications. And so, for example, here 3 plus minus 1 to the n, and I started it at n equals 1. I'm just simply illustrating what happens when you start at n equals 1. I don't have any particular reason here. Okay, so let's see, start at n equals 1. Minus 1 to the 1 is minus 1, so this is 3 minus 1, 3 plus 1. 3 minus 1, 3 plus 1, 3 minus 1. So it ping-pongs back and forth between 2, 4, 2, 4, 2, 4. You know, down, up, down, up, down, up. Okay, and here you can see these are called Bn, and the first ones were called An. So here's a different sequence. And the same thing with the 3, and same thing with the minus 1 to the n. But here I'm dividing minus 1 to the n by n. So if n is 1, for example, if n is 1, then we're looking at a minus 1 to the 1 is minus 1 over 1. So minus, so this is 3 minus 1, and then 3 plus a half, and then 3 minus a third, and then 3 plus a quarter, and 3 minus a fifth, and etc. Another sequence that illustrates much the same thing here, 3 plus minus 1 times 2 to the n. Okay, so this is, again, if you take n equals 1, you're looking at 2 to the 1 is 2. So this is 3 minus 2, 3 plus 4, 3 minus 8, 3 plus 16, 3 minus 32, and etc. And you can see the difference between these two here is that the numbers are kind of homing in on 3 because they're sometimes they're below, sometimes they're above, but each time the over n makes them get closer and closer to 3, whereas here the numbers are in fact diverging from 3. They're headed out toward both plus infinity and minus infinity. For the bottom one, for the closing one, I wanted to illustrate an alternating sequence that alternates not with a period of 2, but I happen to have a period of 4. So I'll remind you what cosine looks like. Cosine starts out up, and then it goes down, and then it comes back up again. There we go. So this is, let's see, 2 pi. So, of course, this is pi. And, of course, this is pi over 2. And it crosses here at 3 pi over 2. So when you look at the defining formula, cosine of n times pi over 2, first you're at 0 pi over 2, then you're at 1 times pi over 2. Then you're at 2 times pi over 2, then you're at 3 times pi over 2, then you're at 4 times pi over 2. And you do indeed see the up, 0 down, 0 up. So it's got a period of 4 and alternates around in a kind of a circular motion. You could make cosine give you a period of size 2, just like the sequences on the top of the slide. You could have a cosine of n pi, so without the over 2. But we're going to prefer the minus 1 to the n. Just you got to set a standard, and that's a standard we're going to use. Okay, so what I like to do, of course, is I like to give some practice problems so that somebody coming to the homework feels like, I got to start. I can do the first 5 at least. So I'm going to give some questions and some answers, and what I urge you to do is pause the video, take out a piece of paper, give it a try, and come back. And when you see the answer, you can tell if you got a good idea of what's happening. So first 5 terms of the sequence, and I'll give you a second to pause the video. Okay, so you're just plugging in I equals 0, I equals 1, I equals 2, I equals 3, and I equals 4, and it isn't hard. Next one. Okay, again, plugging in I equals 0, I equals 1, I equals 2, I equals 3, I equals 4. You see the powers of 3 there, and they alternate sign because of the minus 1 to the I. Okay, next one. All right, and we've seen this one before. It's in this case, it's going to be minus 1 to the 0 is plus 1, so it's going to be up, down, up, down, up, down. We saw a down, up, down, up, down, up. Okay, this is a recursively defined sequence. I find that when I come in and say who has questions on the homework, for some reason the recursively defined sequence often gets some questions, so we're giving you a warm up on those. Okay, great. And when you look at this, you say to yourself something like, well, I know A0. So A1 is twice A0 plus 3. And A2 is twice A1 plus 3. And like that. And when you do the numbers, that's what I got. So 11 is twice 4 plus 3. 25 is twice 11 plus 3, etc. Next one. Okay, you might have noticed that this one starts with I equals 3. I just trying to illustrate starting at numbers other than 0. I mostly do 0, but when you're first introducing something, you want to illustrate a number of possibilities, but it doesn't really make much difference here. So the first thing is minus 1, and then for the second thing, you want to take minus 1 and add 1 to it. Okay, so minus 1 makes plus 1 and add 1 to it. You get 2. Then minus 2 and add 1 to it gives you a minus 1. Minus a minus 1 and add 1 to it gives you a 2, etc. Okay, and this last couple of questions, this is the one that folks often have the most trouble with, is you see a sequence and you're asked to come up with a formula for it. And I'm specifying that the first term in the formula has to have index 0. Okay, please give it a try. Okay, great. A person sees that the numbers on the top of the fractions are all 1, and the numbers on the bottom of the fractions are perfect squares. But if you want to write something like 1 over n squared, you're in trouble because the first term has index 0, and 1 over 0 squared has 2 disadvantages. The first one is that anything over 0 is not defined, but the second is that that's not what you were given to do. So you want to adjust. Instead of saying 1 over n squared, you might want to say something like 1 over n plus 3 squared, and then when you plug in 0, you do indeed get 1 over 3 squared. Okay, next one. Okay, great. A person spots the alternating signs here, the minus, plus, minus, plus. Also spots that the numerators are the powers of 3, and the denominators are an arithmetic sequence difference of 3. So I got this for a formula. You see the alternating signs, you see the powers of 3, and you see the arithmetic sequence. Sometimes, like with the powers here, you might be given, say, a homework question, and you first try I plus 1, but it turns out the things come out exactly the wrong sign, exactly the wrong SIGN, so you change it to I. So that's to say it takes a certain amount of fiddling sometimes. Okay? In particular, isn't this wrong? No, I plus 1 is right. So 3 to the I plus 1, because when n is 0, you want to look at 3. So that's right, I did that right. Okay, last one. Okay, great. We've seen some that alternate before. This is a down, up, down, up, down, up. The only thing is, that might puzzle you is, from where do you alternate? And then the answer is you alternate from halfway between. Halfway between 2 and 7 is 4.5. So I think this is right. Okay. Okay, so we've done sequences. We've done enough of sequences to be able to write down the limit of a sequence, which is the goal for the day. And we're going to define the limit of a sequence, and then we're going to give a couple results about limit of a sequence. And this is hard. I mean, the first sentence here is just simply hard. I'm going to read it and go over it and etc. But I'm just simply going to acknowledge that when you first hear it, you say to yourself, what the heck is going on here? That's absolutely natural. Everybody says that. Okay, so let's see. So the limit of the sequence of ANs is the real number L. None of this is a surprise so far, but now comes the surprise. If for every epsilon greater than 0, that's a Greek letter epsilon, you say it out loud as epsilon. No matter how small, there's an index capital N large enough such that if lower n is greater than capital N, then AN minus L absolute value is less than epsilon. And you're reading that and you go like, what the heck is this? What are you talking about? Okay, fair enough. And we're going to do an example at some length here to describe what the various parts are. But I'm acknowledging that this is not an easy definition. I will say that the second sentence is a lot easier. We are going to write things like the limit as n approaches infinity of AN equals L. I mean, that's the same as the person did in Calculus 1. So that's all not a surprise. We'll say that if the limit exists, then it converges, and if the limit does not exist, then it diverges. And again, all not a surprise, really. But the first sentence is tricky, and I'm going to illustrate it. I think it needs to be need an example in front of you before you can make any sense of it. Okay, so to illustrate, I'm going to take the numbers from the first slide. I took the Taylor polynomials for e to the x centered at 0, and I generated, you remember, a table that had 10 numbers in it. So here is 0, comma, t0 of 2. Here is a 1, comma, t1 of 2, and 2, comma, t2 of 2, and 3, comma, t3 of 2, etc. And come on, it sure does look like the dots are converging on a value of e squared, so it must be the case that the definition suits this circumstance. So the definition says for every epsilon, so I'm going to name an epsilon. The way you make these things concrete is you put numbers to them. I'm going to name an epsilon. I'm going to pick epsilon equals 1 just to pick. I'm going to pick epsilon equals 1 and illustrate what happens. So if you're picking epsilon equals 1, then you're looking at here this picture right here. There's a gold region that runs from e squared plus 1 to e squared minus 1. Okay, it's actually heritage yellow. Anyway, it runs from e squared plus 1 to e squared minus 1. And you can see that although the dots start out outside of that region, at some point they get inside and stay inside. And that's exactly what we mean by a limit. So let's go through the definition, replacing the number epsilon with a 1. Okay, so I'm replacing the number epsilon with a 1. And then the rest of the sentence says there is an index n large enough, and so I think that n equals 4. There is an index n large enough so that if little n is greater than capital N, then the terms, the red dots, are within 1 of e squared. So the red dots are in that region. So if little n is greater than capital N, so if you're looking at greater than equal to, then if you're looking at, for example, A4, or if you're looking at A5, little n is 5, or you're looking at A6, where little n is 6, A7, where little n is 7, those dots are all inside of the gold region. Inside of the gold region. Okay, AN is less than 1 away from e squared. Okay, all right, so the sentence makes sense when you work through it by looking at a number. Now, it's not enough to do one number, really. A person needs a second example, but we've already done sort of 80% of the work. So for the second example, I tried epsilon equals 1. Now I'm going to try epsilon equals 1/10. I mean, so 0.1, just to try. I mean, just to try something different. You could do a 0.0009, but anyway, I'm going to do 0.1. You see how the emphasis here is on epsilon being small. So probably trying epsilon equals 100 would not be all that enlightening. Okay, it says there's an index n large enough, so I got to figure out what the region is. This is epsilon squared plus 0.1, and this is epsilon squared minus 0.1. And so it says there's an index n large enough so that dots past that number, the dots will be inside of the gold region. So when I look here, I think I think 6. I think if you restrict yourself to ANs where n is bigger than 6, so A6, A7, A8, A9, etc. Those dots are all in the gold region. If lowercase n is 6, it's in the gold region. If lowercase n is 7, if lowercase n is 8, if lowercase n is 9, it's all in the gold region. So it says, basically, the first sentence says, once you've worked through the details, you can step back a little bit and say to yourself, the big picture is. So stepping back and saying the big picture is that the first sentence says that from some point on, from capital N on, from some point on, the dots get inside the gold region and they stay inside the gold region, no matter how small that gold region is. So the dots get close to E squared and they stay close to E squared. No matter how close you require, that's how it works. Okay, so the limit of a sequence, in other words, conforms to what our intuition is, that the dots close in on this case, E squared. Okay, I'm going to use that definition of a limit of a sequence to immediately give a result about the geometric sequence. So recall that a geometric sequence of ratio r and initial value a has this form here. So it's just a and AR squared and AR cubed, etc. And the conclusion is, if the r's are small, if the r's are close to 0, if the r's are between -1 and 1, strictly on both ends, then the sequence converges to 0. So for example, if r was 1/2, then you'd have a and 1/2 a, and 1/4 a, and 1/8 a, and etc. Clearly those are converging onto 0. Same thing holds for negative numbers, except that it bounces back and forth around the origin, but it doesn't matter, still converges to 0. If r equals 1, then the sequence converges to a. I mean, if r is 1, then what you've got in the sequence is a. Actually, it's clearly the limit of that sequence is a. If r is -1, then the sequence alternates sign. You're looking at a minus a minus a if r is -1, and so the sequence alternates sign. So unless a equals 0, which is kind of a trivial case, but I included it just to be complete, in which case the sequence converges to 0. So if r is -1, the sequence does not converge unless a equals 0. If r is greater than 1, then the sequence diverges. So suppose r is 2, then you've got a, 2a, 4a, 8a, etc. The sequence diverges to infinity if a is greater than 0, and to -infinity if a is less than 0. And then again, with the a equals 0 is kind of a trivial case. If a equals 0, then it doesn't matter what r is. You just get a. Okay? So we know a lot about geometric sequence, and we're able to make conclusions about it, and we'll use those as we go through the material. I have a couple comments today about places where people get a mistaken impression, and it's bad to get a mistaken impression on the first day because they really can bite you then later on in the chapter. So a couple places I'm trying to caution a person about something happening here. So there is a difference between diverges and infinity. Okay, so this sequence diverges, but it doesn't go to infinity. 3 minus 3, 3 minus 3 diverges. It doesn't converge. The opposite of converge is diverge. So it doesn't converge, so it diverges. But if you think diverges somehow implies gets bigger, well, this doesn't get bigger. It just keeps bouncing back and forth, ping-ponging back and forth between the two values. So there's a difference between diverges and infinity. Another example of exactly the same thing, a sequence can diverge but not have an infinite limit, is this one down at the bottom. 1, minus 2, 4, minus 8, 16. It doesn't go to any single infinity. It bounces back and forth, kind of going to plus and minus infinity, ping-pongs back and forth between those two tendencies. It doesn't go to either of them, so it doesn't go to plus infinity, it doesn't go to minus infinity. We would not say that the sequence diverges to plus infinity, nor would we say that the sequence diverges to minus infinity. The sequence simply diverges. Okay, doesn't have, you can't provide the additional information of saying to infinity because it just is not right. Okay, the case where sequence does diverge because the terms grow without bound is common and important, and I need to give a definition for it. And the definition is slightly different than the definition we gave a minute ago, although it has a similar characteristics. So I'm going to go through it. Same thing. First sentence is tough. Here we go. Where's my pen? Oh, there it is. First sentence is tough. The remaining sentences are all familiar. We're familiar with the limit as n goes to infinity of an is equal to infinity. That's not going to bother us. But the first sentence is tough. For every number capital M, no matter how large, there is a capital N such that anytime little n is greater than capital N, then the ANs are greater than M. So it has something of the same feel at the prior definition, but a little different. And the way to understand this first sentence, just like with the prior one, is to put numbers on it. Okay, so I picked a sequence. The ANs are perfect squares. So this is a 0, 1, 4, 9, 16, etc. So the ends are perfect squares, and I'm going to clearly goes to infinity. I'm going to pick some numbers for capital M, and I don't know, just thought of 10. I'm not picking 10 because it's a super important example. I just thought 10 was a good example, so I picked 10. So what I'm looking here now in the gold region is all of the numbers greater than or equal to 10. So I maybe should somehow put in gold, ... They keep going up all the way. It's not just from 10 to, what is this, 150? It just keeps going up, 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 up. So all the numbers from 10 on up. And now I'm saying that from some point on, the red dots are in the region from 10 on up. And sure enough, if you start from 4 and go n equals 4. If you start from 4 and then go to the right, little n equals 5, little n equals 6, little n equals 7, etc. If you start from 4, the red dots stay inside the gold region. So if you pick 10, and it says there is an n, and that n would be 4, then for any little n greater than 4, the red dots are bigger than 10. Okay? Okay, so it has much the same feel as the prior definition, but a little bit different. And as with the prior definition, I don't like to do one example, so I'm going to do a second example. So I picked 10. My second example is going to be m equals 100. And again, I just simply pluck that out of the air. You see that there's an emphasis here on m being large. But anyway, so I picked numbers that are larger, but really I just plucked it out of the air. So it says that from some point on, the red dots, the A sub n's are bigger than 100. And so looking at the picture, you could say 10, or you could say 11, you could say 12, or you could say 13. I happen to say 11. I thought 11 was slightly clearer than 10. With 10, you have to check whether it says greater than or equal to. But n equals 10 would also work. Anyway, in the example, I wrote n equals 11. And why did I? There we go. Just made a mistake. There we go. So if you took a sub little n equals 12, a sub little n equals 13, a sub little n equals 308, it doesn't matter. All of those red dots are going to be in the gold region, which extends from 100 on up. Okay, m equals 100 on up. Okay? Okay, so although the first sentence is hard, a person can make sense of it by putting numbers into places. Draw a picture, put some numbers into places, and it makes sense. And anyway, it conforms exactly to our intuition, which is that the numbers get big. In this case, big means 100. The numbers get big and then stay big. Okay, so two examples here, an example and a counterexample. Two examples that we have a geometric sequence the powers of 3, and the powers of 3 go to infinity. I don't think anybody thinks that's puzzling. And the other example is the powers of minus 3. And what's happening here, that although they get big, in some sense of the word big, they in fact don't go to plus infinity, because they ping pong back and forth between numbers that are far from 0 in the plus direction and numbers that are far from 0 in the minus direction. Okay? The terms alternate sign. So the first one has a limit of infinity, the second one does not have a limit of infinity. Okay. So I'll just say this is a long video. There's a lot of things to say in this section, and so this might be a good spot if you're thinking that a drink of water is in order. This might be a good spot to pause the video and go get a drink of water. Matter of fact, I'll get a drink of water myself. Now that I say that. There we go. So this is the second half. So let's start in, but it might be worth a break. Okay. So I said several times that I'm going to give a person some warning about mistakes that I see a lot. Not trying to pick on every little thing, but there's a couple places where people often make a mistake, and so I feel like if I say don't make this mistake, I'm saving you some trouble. So here I have a sequence that happens to be made from fraction of two polynomials, and it's nothing particularly interesting about it other than that I can't start with 0 because otherwise I'd have 0 on the bottom of the fraction. But other than that, there's nothing interesting. What I'll often see if I give this problem in class, and I'll walk around looking at small groups, what I often see is that people somehow will say to me, well, I'm looking for the limit as I goes to infinity, so I'll plug in infinity. And I don't know who taught them Calculus 1. I hope it wasn't me, but they got a crazy idea. Okay, that person will do the following. That person will say something like, well, infinity squared is infinity, and then there's infinity, and then there's 2, and then down on the bottom, infinity cubed is infinity, and then there's infinity, and when you add 5 infinity to 3 infinity, you can ignore the 2 because it's infinity. You get 8 infinity, and when you add the 2 infinity to you get 3 infinity. Oh, this makes my head hurt. Oh no, this is so not right. So do you see, I was very careful to say this is wrong. Don't do that. For one thing, it gives the wrong answer. The right answer is not 8/3. If you try any reasonably large number, you don't get 8/3-ish. You get a value that's very close to 0. For another thing, it applies methods that just are simply not justified. You can't do that. You can't do arithmetic on infinity the way this person is trying. So don't do that. Instead, we need some laws, some rules, and here they are. Okay, so there's a lot on the slide, and it's really, I like to put everything on one slide. I'm kind of a joiner instead of a person who breaks it up into a splitter, a person who breaks it up into separate things. But nonetheless, I'll go over it quickly. So first is this comment that I'll talk about in the next slide, that A and a B and those sequences converge. Second, to go through the laws quickly. So the very first one, this says the limit of a typical sequence, n goes from 0 to infinity, exists if and only if the limit for n goes from capital N to infinity. So for example, n goes from 100 to infinity, or n goes from 1,000 to infinity, or n goes from 1,000,000 to infinity. So that is to say that the limit of a sequence is about the tail of the sequence. It's about all the numbers past capital N, all the numbers past, say, 100, all the numbers past, subscript of 1,000, all the numbers past, say, a subscript of 10 million. So the initial terms in a sequence aren't really what decide whether the sequence converges. It's the tail of the sequence. Okay, but so then the second sentence says the limit of a constant sequence is that constant. I don't think this is a surprise. We saw this kind of thing in Calculus 1. If you had a sequence that went 7, 7, 7, etc., does anybody surprised by the fact that the limit is 7? Next law, and again, this will remind you of the limit laws that you saw in Calculus 1. Next law says you can bring out a constant. So if I had something like the limit as n goes to infinity, these are discrete limits, but nonetheless, the limit as n goes to infinity of 3/2, say n squared, why it's perfectly correct to, I meant 1 over n squared. I apologize. 1 over n squared. It's perfectly correct to bring out the 3/2. 3/2 times the limit as n goes to infinity of 1 over n squared. Okay, so you can bring a constant out past the limit sign, and again, saw that in Calculus 1. I don't think that anybody's going to be surprised by that and say, wait, what is this? Third, limits break along a plus, and limits break also along a minus. Fourth, limits break along a times, and limits also break along a divided by. Except, of course, you got to watch out for divided by 0. But nobody in all the years I've been teaching, nobody has ever said to me, what do you mean you have to watch out for divided by 0? Everybody's got that already. And the last one, though, is the one that might be something that a person has not got their kind of antenna up for things to watch out for. This says you can bring a power out past the limit expression. So if you're going to look at the limit of n squared, you could find the limit of n and then square it. But there is a sort of clause here. It says where p is greater than 0 and an is greater than 0. So what's happening here is that you're worried about something like, what if an was minus 1? What if this limit was minus 1, and the power was 1/2? Then you'd be taking the square root of minus 1, and in this class we just don't focus on complex numbers very much, so we left that case off of the correct things to do because we're not willing to go into kind of what to do. There are things you can do in complex numbers when you take limits, but we're not going to do it. Okay, it's just outside of our scope for the class. Second, I'm going to go on to the next slide here, but just reminding you what this beginning phrase says. Assume that the sequence of ANs and the sequence of BNs both converge. So the next slide says those laws are prefixed with that sentence, and I'm going to caution you that that's not a throwaway line, that actually we need that. So if you look at this sequence here, for example, it's going to be 0 minus 0 over 2, followed by 1 minus 1 over 2, followed by 2 minus 2 over 2. I mean, clearly it's a sequence of zeros. So clearly it converges to 0, all good, all good. But if you had tried to apply Rule 1 and split at the minus sign, then you would have gotten a sequence here and a sequence here, both of which go to infinity. I mean, a 0 over 2, 1 over 2, 2 over 2, 3 over 2, 4 over 2, those numbers are going to infinity. So you would be saying to yourself something like 0 equals 0 equals, infinity minus infinity equals 0, and we know that our experience with L'Hopital's rule says that that's nonsense. So what's going wrong here is that this is a divergent sequence, so not converge. Sorry about the handwriting. It does not converge, so we need this sentence. This sentence matters. Okay, so we have to have our antenna up for not breaking up unless the result converges. Okay, so there's a couple places in this course where you run across sort of, third rails, things to watch out for, things that can bite you, and this is an example. Okay, and again, I like for folks to feel like when they come to the homework, they have some idea how to start with the first couple homeworks, so I'm going to do those as quick practices. Okay, please, first one. Okay, great. I think, a person sees that I'm going to apply some simple rules, so they're thinking I'm going to bring the 4 out past the limit sign, right? That makes sense. And I'm going to bring out the power, and then I'm looking at I plus 5, and now in this case, I plus 5 goes to infinity, but we're good because it turns out that the square root of I plus 5 is also infinity. The square root is, and the 4 is infinity, and so we're good. Okay, so we're willing to bend a little bit there. Next one. Okay, and here if you think you're going to break along the addition sign and you say to yourself there's a 3 and there's a minus 1 to the j, 1 over j, and because the 1 over j's go to 0, then this entire limit is 0, and the limit of the constant is 3, and so we're just simply looking at 3. For the next one here, there's 1 0 and then 2 zeros and then 3 zeros. Did you notice that? Okay, please. Okay, great. What's happening here is that there are getting to be increasingly many zeros in the sequence, but nonetheless, there's always going to be a 1 to come. So the sequence will not settle down at 0. It just, every once in a while, there's a 1. So no matter how large the index, there remains to come in the sequence both zeros and ones, so the sequence never settles down into value. It does not converge, and if it does not converge, then the right word is diverge. Okay, so the right word for does not converge is diverge. It's not that you say somehow there's an intermediate state. Okay, so we're ready. We've got the definition of the limit of a sequence, both in the case of infinite limits and finite limits, and we're going to finish up the section. There's a good bit to go, but nonetheless, we're going to finish up this section by listing some consequences of the definitions. So the first consequence that we're going to need is the squeeze theorem. Suppose that you have two sequences, the ANs and the CNs, ANs and the CNs that both have a limit of capital L. Maybe capital L is 12. So both sequences go to 12. And the BNs lie between them. So for example, you have A0, B0, and C0, and the B0 is between the two. And you also have A1, B1, and C1. So on a term-by-term basis, B2, C2. On a term-by-term basis, the B's are between the other two. Okay, then the B's have the same limit. The B's must also go to L. They're squeezed by the other two to go to L. And just to take an example, if you're looking at this particular sequence, n factorial over n to the n power, I've tried to pick an unfamiliar one, n factorial over n to the n power, and we're obviously going to somehow get it that it's squeezed. So I took the term a sub n, and I got here, I rewrote it as n factorial on the top and n to the n on the bottom. There we go. And now I've got a 1 over n, and everything past 1 over n, that's less than or equal to 1, that's less than or equal to 1, all the way out to less than or equal to 1, and that one equals 1. So the first factor is 1 over n, and it's multiplied by a number of other factors, each of which is less than or equal to 1. That is to say, an is less than or equal to 1 over n. So I get that the sequence of ANs is squeezed here. On the one side, it's less than or equal to 1 over n. On the other side, it's greater than or equal to 0. The sequence of zeros obviously converges to 0. So the limit of this sequence here, the limit of the starting sequence, must be 0. So the terms are squeezed between two values, each of which we know where they go. And an important corollary, that important consequence of that is that if you know where the absolute values of a sequence go, if you know they go to 0, then the sequence itself must also go to 0. And we already said that the sequence of absolute values goes to 0, and obviously the negative of the sequence of absolute values must also go to 0. You could bring the negative out past the limit sign. And so the ANs are squeezed, and so they must also go to 0. Okay, but so we still find ourselves with that list of rules, and a person can say, this is going to get annoying if we don't watch it, because we're going to be ending up doing consequences of those rules that take, 20 minutes to do each problem. I wish there was a shortcut, and there is a shortcut. Person is saying, I wish there was a way to utilize what we already know, to leverage what we already know, to take what we already know and use it in this case. And so there is. So the distinction that we're trying to make here is that sequences are discrete. There's an A1 term and an A2 term, but there's no A sub 1.234. They jump discretely. So there's a genuine difference between what we did in the Calculus 1 class limits and what we're doing now. Nonetheless, we're going to try to leverage something that we know from Calculus 1. So if we look at a sequence like the fractions that we looked at a few minutes ago, then we can't apply L'Hopital's rule, because L'Hopital's rule calls for us to write down derivatives. I can't take the derivative of a discrete, because it says f of x plus delta x minus f of x over delta x. Wait a second. So I got to take delta x to be like a 0.1, 0.01, 0.001. I can't do that in a discrete context. I can't do that. There is no a sub 1.001. There just isn't one. So I can't do that. So I can't apply L'Hopital's rule, because you can't take derivatives. Okay, but nonetheless, I can kind of apply L'Hopital's rule. I can convert so that L'Hopital's rule applies in many circumstances. So the theorem says, consider the real number function f and suppose that it has a limit. Suppose that it has a limit from Calculus 1. You figured it out. Then the sequence of numbers where you plug in natural numbers 1, 2, 3, 4, 5. Not 1.001, 1, 2, 3, 4, 5. You plug in those numbers into f. That sequence has to have the same limit. And the obvious example to do of the theorem, I'm going to talk about why the theorem is true on the next slide. It just didn't fit on this slide. But the obvious example is if you take the sequence above here and you consider this function here, I convert it to x's to illustrate that it's a real number function, a regular calculus 1 real number function. And we can find that limit. You know, I said L'Hopital's rule, but you can find the limit in another way if you like another way. Anyway, we get that it goes to 0. Okay, so by some calculus 1 method, you figure out that that limit of that is 0. And then the sequence of what happens when you plug into f of 0, f of 1, that's a sequence of discrete values, f of 2, f of 3, that's a sequence of discrete values. That sequence has to have the same limit. The limit happens to be 0. So the theorem says if you know where the continuous function goes, then you know where the discrete sequence goes. And the next slide shows a picture, and really the picture is wholly convincing. I'm going to come back to that convention. The next slide shows the picture. The picture is wholly convincing. This is a graph of f. Okay, and the dots are, of course, the sequence elements like they were in previous slides. So this is going to be, you know, a sub 1, a sub 2, the y value is a sub 2, a sub 3, etc. If the function goes somewhere, it sure looks in this picture like the function is going to 0. If the function has a limit, then the dots have to have the same limit. The function goes somewhere, the dots have to follow. They have no choice. Okay, so the theorem basically says if you know the continuous case, then you can conclude the same thing for the discrete case. It doesn't say the opposite. In fact, the opposite doesn't hold. But it says if you know the continuous case, if the function has a limit, then you can conclude the same limit applies to the discrete case. Just a comment here down at the bottom, just a comment, that the convention is to write the continuous function, to write the real number function with letters late in the alphabet, x, y, and z, basically, and to write the integer expression here with numbers in the middle of the alphabet, letters in the middle of the alphabet, I, J, K. And that's a pretty strong convention. If somebody writes, you know, on one of the homeworks, if it says something like a 5i squared, that probably they mean I is restricted to integers. And if they write 5x squared, probably they mean that x can be any real. Okay, I will, before we go on though to do the problems, I will comment that sometimes we have trouble leveraging continuous functions. Sometimes we're going to have it's going to be an issue to convert to x's. So a first example is minus 1 to the n. If you said to yourself something like, well, I'll just consider minus 1 to the x, where x is a real number. Fair enough. What if x was 1/2? Then you'd be looking at the square root of minus 1, and that's complex numbers, and we don't do that here. We're going to talk about complex numbers a little bit, but that's mostly beyond our remit. Another place is factorials. Okay, so the factorial function, at least on its face, is discrete. You know what? I can make perfectly good sense of the 5 factorial, 1 times 2 times 3 times 4 times 5. What do you make if I was to say the factorial of square root of 7? Well, so we're calling that beyond the scope of this class. Okay, so while there are many sequences where we can find the limit by considering the related continuous function, that's not true for every sequence. But obviously the homeworks that say apply the theorem, well, it applies. So again, the theorem says if you have a real number function that has a limit, then the associated sequence must have the same limit. Okay, let's try. Oops, sorry, one too many clicks. Okay. Again, I'm going to pause. I urge you to pause the video, give it a try, and I'll come back and give you an answer. Okay, great. So you consider the real number function of replacing the j's with x's. And, you know, the limit of that function is infinity. One way you can find it is with L'Hopital's rule, but if you like some other way, then do the other way, great. Therefore, the sequence also has a limit of infinity. Okay, next one. So we saw this one earlier. It's got the -1 to the j in it, and I've just cautioned you on the slide before that you can't just say -1 to the x. That's just not okay. But you can say things like, we know from Calculus 1 that 1 over j goes to 0. And then because the two halves, the 3 and the -1 to the j, 1 over j, both have a limit, then we can split along the plus sign, and there we go. The sequence as a whole converges to 3. Next one. Okay, I don't see why you can't consider the associated real number function 5 minus 3 over x squared. You could get a common denominator, whatever you like, take the limit. I would apply L'Hopital's rule, but if you have some other way that you like better, go for it, and you're done. Okay, basically 3 over j squared goes to 0, 5 goes to 5, and the answer is 5. Last one. So this one might be a head scratcher for some folks, and I think the trick here, the technique here, is to you say to yourself, it's got factorials, and I can't write x factorial because what if x is 7 square root of 7 kind of thing. But if you just simplify the expression first, let's try, for example, j equals 4. Then I've got 5 factorial on the top, 1 times 2 times 3 times 4 times 5. And on the bottom, I've got 4 factorial, so 1 times 2 times 3 times 4. And there's a whole bunch of canceling, and I'm just left with 5. So basically, AJ is a somewhat, confusingly written j plus 1. Okay, so when you notice that AJ simplifies to j plus 1, now it's easy. Simplify the fraction first, you get AJ equals j plus 1, and clearly the limit there is going to be infinity. I mean, you could convert to x's. Do you really need to? You could convert to x's and get that the limit is infinity. Okay, a couple more results. Still more to do, but getting closer to the end. I recognize that this is a long section. So a sequence is bounded above if there's a number m larger than all the terms. So if there's a bound. And sequence is bounded below if there's a number m which is less than all the terms. So there's a lower bound. In either case, you call it a bounded sequence. A convergent sequence is bounded both above and below. And I happen to pick here, for illustration, 5 times cosine of n over n. And the thing about cosine of n, of course, is that it bounces up and down. The thing about divided by n is that it makes the numbers smaller. So instead of bouncing up and down to plus and minus 5, this is going to bounce up and down and gradually center in on 0. So at the beginning, it has some numbers that are, for example, more than 1 away from 0. But from some point on, they become within 1 of 0. And then they become within a half of 0. And then become within a third of 0, and etc. So when I say the sequence is bounded above and below, what I mean is that from some point on, you're definitely not unbounded. And the initial terms just give you a bound. In this case, the bound seems to be 2.702 above, and below seems to be minus 1.650. Okay, so a convergent sequence, because it converges on some limit, a convergent sequence is bounded both above and below. And again, some more vocabulary, and this slide obviously relates to the previous slide, but a sequence is increasing if the terms go up. I mean, a sequence is decreasing if the terms go down. Either of those two cases are called monotonic. And the theorem is that an increasing sequence converges if and only if it's bounded above. Similarly for a decreasing sequence and bounded below. An increasing sequence converges if and only if it's bounded above, for the simple reason that, if you say all the terms are less than 10 and they're going up, well, they got no place to go. They have to at some point hit the ceiling. So it's got to converge. Okay, so we're going to close with some practice, and that'll be the end. I recognize it's been a long video. Okay, so let's try it. ln of n over n, and I'll pause for a second. Okay, so I think there's no reason why you couldn't convert to x's. Try ln of x over x. I use L'Hopital's rule, but if you like some other method, then go for it. As x goes to infinity, f of x equals 0, so the limit of the sequence is also 0. Next. Okay, we've the minus 1 to the j, we can't just change to x's. So if you're saying to yourself, well, this is a method to solve all problems, no, it doesn't. But nonetheless, you can write down that the sequence is 4 minus 2, 4 minus 2, etc. So obviously it does not approach a limit, so it diverges. Next. Okay, I think that we can split along the plus sign. And splitting along the plus sign gives me a 5 over n and a 7 over n squared. And I mean, you could, if you like, convert to x's and apply L'Hopital's rule or something. You can simply say it's clear that 5 over n goes to 0, and it's clear that 7 over n squared goes to 0, and so we end up with a total limit of 0. Next. So this is like the last one. The minus 1 to the j makes it awkward to convert to x's, but you just say to yourself something like 1 over j to the 3/2 power has a limit of 0. So if we were to split along the minus sign, we'd have two convergent sequences, a sequence of 2's and a sequence that converges on 0. And so the overall limit is 2. Okay, next. Okay, great. It seems to me that I can absolutely split this into 3 to the n over 9 to the n minus 5 to the n over 9 to the n, because 3 over 9 to the n and 5 over 9 to the n each converge to 0. So I've got two convergent sequences, and I get a total of 0. Next. Okay, so if you try to convert this one to x's, you find yourself in a bit of a pickle, because cosine of pi times 2x plus 1 is just going to go up, down, up, down, up, down, up, down, and not have a limit. That does not mean the sequence doesn't have a limit. Instead, what the theorem actually says, I won't click back, but what the theorem actually says is that if the function has a limit, then the sequence has a limit. It doesn't say if the function does not have a limit, then the sequence also does not. It does not say that. So we're down to looking at what actually happens when you plug in the numbers. And when you plug in the numbers, you get a sequence that goes minus 1, minus 1, minus 1. Well, there you go. Okay, two more. Next one. Okay, so there's no reason you can't convert this one to x's. So that solves a lot of problems. It doesn't solve them all, but solves a lot of them. So x to the 1/2 over x to the 1/2 plus 3, and L'Hopital's rule gives you a limit of 1. Last one. Okay, so with this one here, there's no reason why you can't bring the 5 out. And then you're looking at e over 2 raised to the nth power. And I would just say e is 2.718, so 2.718 over 2 is a number bigger than 1. So when you take the powers, it goes to infinity. So we sometimes find ourselves looking at the sequence, and we sometimes find ourselves converting to x's. So there's a variety of ways to solve it. Okay, very good. Been a long video. So I'll pause, and we'll see if for the next section does the definition of series. So we're really getting into the meat of it then. Very good.